So welcome everyone to the Winds and Currents webinar. Today we're fortunate to have David Long, who's going to talk about potential for measuring ice from scatterometry. I'll let you go ahead, David.
Okay, let me see if I can get my share screen up here. So I'm grateful for the opportunity I have to kind of talk a little about this. This is something that's pretty cool, pun intended, to talk about, something a little different to follow on than this. So in looking at the Odyssey mission, of course, we're really interested in the wind problem. That's the real problem. But we also end up collecting data elsewhere in the world, just like we've done with the other wind scatterometers. So this allows us to sort of extend the utility of the Odyssey mission by other applications, sort of secondary applications, as we've done with some of the scatterometer things. Some of those include land, where we can do vegetation and even wind by looking at sand dunes. But I want to emphasize a discussion on polar applications, where I'm going to sort of talk about a few things about sea ice mapping and glacial ice, icebergs. And I want to talk about how we can actually measure wind over certain areas of the great ice sheets as well by looking at the shapes of those there. Now, the advantage of a scatterometer for polar observations as compared to some other sensors is that the backscatter itself is extremely sensitive to liquid water. And this is even more so for KU band. That means we can discriminate these many features and do true geophysical science with the data. So this is exciting. We get this global coverage. The Odyssey will add some new frequencies, the Ka band to the system, and extend the time series that now goes back to 30, almost 40 years now, so that we can start doing serious climate studies on this. It also, compared to previous missions that have looked at Ka band, they've all been radiometers, they're very low resolution. Odyssey will provide much higher resolution, which will make a huge difference in some of the science we can do. Now, compared to SAR, it doesn't have the same resolution, but it has coverage and has frequent daily coverage, which is something that's difficult to get with the SAR system. So just a little bit of background. Here is just a typical scatterometer showing that we get multiple passes per day in the polar region. So we get global coverage in the near the poles each day. And if we extend that to include multiple days, we get full kind of global coverage. Well, we can exploit that coverage by looking at the polar region. So here I've got an image on the left, which is an L-band scatterometer observations of Antarctica. And the right, I've got a dual frequency, C-band and KU band operating together. And even a casual examination of this animation shows some really spectacular kinds of things. We can see icebergs, we can see the movement of sea ice, and the stuff that we're normally interested in, the winds, are actually the noise in this sort of polar ice process, that stuff that's going around on the outside. So we'll look at that a little bit further in some of the applications here. So here's a false color image combining C and KU band, basically one frame of that the movie I showed a moment ago. And in it there, in the Weddell Sea, which is the upper sort of purplish area up there, those bright spots are icebergs. The different scattering mechanisms that vary across the ice sheet cause the glacial ice to kind of golds and browns, kind of a beautiful color there. The sea ice varies in purples and gold. This is because the scattering mechanism is different at each of the different frequencies. Ka band will add additional information because it's looking primarily at the upper surface roughness, which really is an area where we're really interested in getting more information about, because we can remove that surface roughness from lower frequency observations to look deeper into the ice. So this is a KU band image that we collected, the very first image from the CSAT scatterometer. In it, there was the iceberg, B10A up in the upper left, and that led to kind of the applications of scatterometry. Notice how I've actually had to mask the wind out, the stuff we're primarily studying with Odyssey, so we could do some stuff on that. Here's what that an iceberg like that looks like from the ground level, from a ship up in here. We've often used the real-time capability of the iceberg to navigate ships to these icebergs, where the iceberg acts as a biological island an oasis because the nutrients that have been captured in the dust, in the accumulated glacier ice, they melt, fertilize the ocean. That brings in all the phytoplankton, which causes in the other animals, and pretty soon we get a whole bunch of animals around that. So biologically, icebergs are very important in the South Atlantic and South Pacific down there. Well, that led to the applications of tracking icebergs. And so I've got an animation, some of the stuff that we've done here at BYU. And I have to toot my own horn on one little detail here. The picture in the lower right is from a paper recently published where we cited work from the 1700s, literally from the year 1700. So I have this ancient citation we got to put in where we compared icebergs observed in the 1700s versus today, finding that there was a compatibility with that overall process. The iceberg that we have of interest recently was iceberg A68, which was a very large one that broke off the Larsen ice shelf, floated out there. If you look at the animation, you can see the growth and the freezing of the sea ice, and you can watch that iceberg move northward and finally into the Scotia Sea, right, moving out of the Weddell Sea. And you can notice as you look at it that it changes from light to dark. What you're observing is the change in the backscatter, the sigma naught of the surface due to the presence of liquid water on the surface of that ice sheet. Okay, so the signature is extremely sensitive to the melting conditions. Where are we going with this a little bit? Here are two images, synthetic aperture radar images, collected on the edges of sea ice. The thick bars, the black and white, represent current estimates of where sea ice comes from using passive sensor radiometers. The SAR data, which is much better at defining the ice edge because of its resolution, is just not available all the time. So we have to rely a lot on these passive measurements. But as you can see, they're much coarser and cruder, and they don't actually show the ice edge very well. Here's where the active data becomes particularly valuable. Active data has a distinct contrast between open water and ice due to the dielectric constant of the two differences and the roughness of the sea ice. Furthermore, the radar has a much higher resolution, which allows us to get closer to the edge. Now, in the radiometer, they sort of define an edge as being some percentage of the ice. That's what they call it. But the reality is it's just a linear interpolation between the emissions from the ice and from the ocean. But the radar, by looking at the backscatter, gets a much more discrete and, I might point out, less tunable ice edge, even though there are issues with sharp edges on the right versus the more diffuse edges in the images on the left. Again, this is where the scatterometer data is particularly useful. The contrast between ice and ocean is even higher at Ka band, which is really kind of exciting from the point of view of looking for this, because we're going to get much higher resolution plus that additional capability for Odyssey. Now, this water sensitivity leads to some really interesting applications of the backscatter data. Now here, because it's easier to see, I've got optical images of the breakup of the Larsen ice shelf. The Larsen ice shelf had existed along the Antarctic Peninsula for at least 10 or 20,000 years. And about the year 2000, that ice sheet shattered and just disintegrated almost explosively. Well, one of the hypotheses that we've been testing is that as the ice sheet, or as the temperatures warm up, liquid water forms on the top of the ice sheet, which is accumulated snow on top of either sea ice or just the glacial pieces that come out. Water percolates, meltwater percolates down into that snow, refreezes, which puts stress on it and expands cracks. That structurally weakens the ice, which explains the reason why it explosively done on that. Well, understanding that surface melt and being able to map it in real time is critical to understanding this sort of a process. One of the reasons that I've been involved in the study of icebergs is because we use the icebergs as proxies for the breakup of these ice sheet shells. This melt could be used this scatterometer could be used then to map the extent of the melt, how intense it is, by comparing with radiometer data and other applications. So here's where the Odyssey data can supplement passive data and in a complementary sense, as well as other frequency data, to really help us understand and improve our understanding of what's going on in the ice shelves. Now, I might point out this particular image shows just the melt days just before the breakup of the ice shelves, but about half the ice shelves that are shown here, the colored regions on the left, are gone now, with some that are stressed out, including the Wilkins ice shelf, which is the one that's down on the left. It's apparently breaking up right now. So here's that process that we use, kind of creating an animation of that process. In the interest of time, I'll just let you look at that for a second, move on. Those big white blobs up to the upper right are in fact icebergs that are moving away, that have broken off that ice shelf as it's collapsed. Now, one of the things that's very interesting is that, particularly in Antarctica, the altitude at the South Pole is really quite high. It's nearly 8,000 feet or more, is on top of all that snow on there. It's very cold. That cold air settles and then flows out over the continent. These are called the katabatic winds. It's primarily just a settling of the cold winds. And that produces very steady winds over most of the continent. Those winds disturb the accumulated snow and produce sastrugi, which are small scale snow dunes. There are also some very large scale dunes as well. That results in a variation in the observable backscatter versus azimuth angle, which means by observing from the scatterometer for multiple azimuth angles, we can actually infer the wind direction. So this shows the modulation of the backscatter, the blue, and then we estimate the wind direction using a simple bi-frequency Fourier series here, and then we can correct that and flatten that curve. And from that, knowing the directions, we can produce those streamlines, giving us wind direction over Antarctica. Now, this is pretty steady, but we're watching some changes in the patterns, and at Ka band, we're going to be much more sensitive to short time variations, which may allow us to do, rather than kind of a mean wind, maybe see a seasonal effect of winds up in there. So scatterometers not only do wind over liquid water, they can do wind over solid water. So here's an example of some of the extracted winds that we've produced from Greenland using the same approach from NSCAT, ERS. We've done some of the other scatterometers. This is compared to modeled winds over the surface. Over on the right, we see a not perfect comparison with the NSCAT data, but the ERS is particularly well suited for modeling that process. This is particularly important in some recent research where the warming conditions in Greenland are resulting in meltwater percolating down in the snow and accumulating as aquifers. That is liquid water in this saturated firn that can store water, and this can also percolate further down, lubricate the basal interface between the ice and the ground underneath, the rock underneath, and causing a much greater loss in Greenland. So I'm working with some collaborators on understanding this aquifer melting in Greenland, and this also occurs in Antarctica, which affects both the stability of the ice sheet and the melting rate. So this is a kind of a newly understood mechanism for why Greenland is melting at a much higher rate than had previously been anticipated. So returning back to this idea of Greenland, Greenland's piled up with 2 miles of snow at the top. Okay, at the very highest level, that snow never melts. It's the dry snow zone. Because of the weight of that pushes down and it flows off to the edges as glaciers, and the snow packs down, becomes firn. The firn becomes then ice when it gets sufficiently deep. As you move downslope from the edges, it will melt occasionally. That meltwater will percolate down the snow, refreeze, and then occasionally it'll produce the saturated snow, these firn aquifers we've talked about, and which will then run off and form in that. Well, the scatterometer data, lower frequencies penetrate deep in the snow, so we can get some history. The higher frequencies give us more surface conditions. And at Ka band, we will be able to look at the very small scale changes, small temporal scale changes, excuse me, that were the melting conditions that we could couple with lower frequency data so we could understand the intensity of the melt during the season, something that's relatively difficult to do with other sensors on this. So this is a way of kind of looking at the bellwether of the climate, Greenland, and its applications. So on the left, I have a L-band image made with the SMAP L-band radar system. It had both a scatterometer and a synthetic aperture radar, so we have both low and high resolution data. But with its multiple azimuth capability, we can extract both the wind direction and look at it. On the right, we have the C and KU band example that I showed earlier. Notice the differences in some of the features. Now, along the edges, that colored zone is where the melt occurs. I'll talk about that in a moment. But if you look off to the left of Greenland, in the dark area on the right image, but on the left image, you can see sea ice. And those sea ice, we can see some conditions in there representing the surface roughness and the thickness of the ice, which we could extract from the data. That isn't as easy to see in the higher frequencies because they don't have much surface penetration. But the problem with the lower frequency data is that it's contaminated by the surface if you want to see the thickness. So we need a combination of both high and low. Odyssey will provide new information on that. Here's a time series looking at KU band, which is the closest long-term time series I have to KA, showing a summer melt. During the winter, the small scale crystals, the fern that make up the snow that accumulates on Greenland, have a lot of backscatter due to volume scattering. Around the edges during the summer, as melt forms, it dramatically changes the dielectric constant of the snow. As liquid water forms on the snow crystals, the dielectric constant shoots up, which means you get a lot of backscatter, a lot of scattering, forward scattering, excuse me, which means we get less backscattering, so it becomes dark. And then eventually, as the winter progresses, it refreezes. This makes the scatterometer data particularly sensitive, as I've said multiple times, to the melting conditions that we want to look at that. And we can use that to do climate studies. So here's an example over a 30-year time period, and we've extended this now, showing changes in Greenland. Now, to produce this image set, I took the mean of all the data over all these years, collected on a particular day in the winter for Greenland here. And then this is the anomaly, the difference in backscatter values. So if we look at kind of the differences, the melting conditions, which cause refreeze, as the water goes down into the snow, it eventually refreezes. That creates ice features, ice lenses and glands, which have a much higher backscatter and therefore look brighter. We can see that melting is more common in 2008 than it was in 1978. We can see a trend of increasing melting conditions. Paradoxically, the upper areas where it's dry snow, it doesn't get a lot of melting. As we get more snow, the snow accumulation buries ice slabs that occur in the summer, which are due to winds. It causes a kind of a thin ice layer just right on the very surface. Those get buried, and so the backscatter drops at the high altitude. So the change as we go from 1978, where it's low, to the large backscatter to the lower backscatter in the modern times, corresponds to additional accumulation. So that's actually consistent with the general warming conditions because there's more moisture in the air, which results in more accumulation. But there's also more melting. That melting is continuing to accelerate as measured by this and other sensors that could directly measure the amount of water coming off of Greenland by looking at gravity changes, show that the Greenland is melting very rapidly. So here is Greenland in context. We're watching this multi-frequency time series of data, and the center ice edge there is the permanent ice cap. This is multi-year ice present now. It grows out during the winter period, and then as the summer comes, the waves of warm air melt the surface, which changes the backscatter value, makes it a little more purple or darker in these images. And you're actually seeing the atmospheric flow here. We were talking about atmospheric rivers later. These are sort of atmospheric warm fronts moving across the ice sheet. We can also see the advection of thick multi-year ice, that lighter golden color, down the east and west coast of Greenland into the North Atlantic. These represent a significant freshwater flux into there. And this advection is one of the reasons why the northern polar cap is actually thinning due to the movement of this ice. Now, SAR data can provide similar data to this, but it's difficult to provide global images. And if we look back into the past, the scatterometer data is the most active data we have. It goes back long enough. So to do climate series, this is the data we have. The Odyssey will provide a much higher resolution version of this on a daily basis, which then can supplement lower frequency SAR data, but that isn't available always globally. So this is going to be an important data set moving forward to look at for looking at this process. Now we can analyze what I just showed you more directly, and I'm kind of just sampling this, so it's sort of a hand wavy thing here. But this sensitivity allows us to look at the backscatter. So what I've done here is create a histogram of the backscatter values over ice, removing land and open ocean, okay? And just done a backscatter value for each day. So you can imagine this histogram for each vertical line on that image in the upper right. During the summer time period, August to September, there's a lot of melt, there's not a lot of ice. And what we're mostly seeing is multi-year ice that is a lower backscatter because it's got surface melt on. That then refreezes, so the backscatter comes up during September, refreezes, and the multi-year ice stays bright across the rest of the year, okay, until it remelts there. So that's the topper level, the top thing. As new ice is formed, first year ice, FY, the backscatter value tends to be lower, but the area gets larger. So from the normalized histogram being shown here, we see the first year ice, which drops down, becomes very wide down there at a very low value, increases on there across the bottom there. In the lower left, I've got a kind of a 3D view of this histogram. This gives us a very natural way of discriminating between multi-year ice and first-year ice. Well, multi-year ice is thicker and therefore has a much greater insulation capability between the cold Arctic air and the ocean. So you get less formation, less heat transfer. The first-year ice, which is much thinner, offers less insulation, so you get more heat transfer between the ocean and the atmosphere. That affects that. So we can do this for each year of a time series. So I've taken the histogram now and turned it around and done it for multiple years. So remember, the multi-year ice is kind of on the right over here. The first year ice is on the left. And if I compare that plot on the left with the extent of the sea ice, which is shown on the right, so that blue line represents the area of ice coverage in the northern hemisphere. During the summer, it's on the left, so you get the minimum, and on the right, you get the maximum during the winter. Now, if we look at this time series this is a relatively short time period. There are longer ones here, but it's harder to show over on a plot like this. During this time period, the winter ice maximum is about the same, but the summer ice is dropping. The minimum period is getting less and less coverage, which means there's less multi-year ice being available to begin the start of the winter, which is affecting the thermal transfer between the ocean and the atmosphere. So warming in the atmosphere is now being transferred into the Arctic Ocean, which affects the thermal environment and therefore the thermal haline solution in the North Atlantic. And now we're getting into the deep oceanography that this data is providing information, or this is informing those sorts of processes. So here is kind of a snapshot of first year ice versus multi-year ice at the peak of the winter, same day each year. We can see the 2003, the white area, which is the multi-year ice, the thicker ice, the greater insulation. The light cyan is the first year ice. We see the multi-year ice covers a large percentage of the pole, but over time, doing that advection down there on Greenland, we see the multi-year ice is being reduced. So the circulation up there is resulting in a change in over a decadal period of the freshwater influx to the North Atlantic and to the thermal environment in the Arctic Ocean area. So this is some representative science, just a couple of things just for fun, show you a lot of pretty pictures about the kind of science that can be done with the scatterometer data, with an instrument that was never designed to do polar observations, but with the appropriate use of the data, we get this extra science for free. So, any questions?
Thank you so much, David.
I pushed that through really fast because you wanted a long discussion.
Yeah, and discussion is great. I have lots of questions, and I'm sure other people do too. I think I wanted to start by asking about the program of record, and you've said Odyssey as Ka band will be great in tandem with other missions. What do you think are likely to be flying in the time frame we might have Odyssey?
Well, we know, for example, that a lot of radiometers will be flying. So we'll have, wide band. Coming up is the Europeans will be launching Simmer, which is a radiometer, which is has very low to very high. So there will be some expanded capability of radiometers besides the existing SSMI, SSMIS time series that goes back multiple decades. I believe we'll continue to have A-scat, C-band scatterometers flying for the next few decades. Those are the plans coming out of ESA. That'll give us C-band capability. If we combine the C and the Ka band, we will have a really nice spread. We're hoping to get an L-band instrument up to do SMAP follow-on in the future. That's not program of record at this point, but one can hope. We do have NISAR going up and a few other kinds of sensors in the futures. Hopefully the Indians will continue to fly Ku band scatterometers, so we're going to continue the scatterometer access. So I anticipate that we're still in the golden age of scatterometry.
That's really good. Looks like there's some hands up. Fabrice has his hand up, and there's a question in the chat from Christine Cohen-Ginger. So why don't we start with Fabrice, and then we'll go to Christine.
Hi, yes, very nice talk, and amazing to put that all together. Iceberg ice sheets and sea ice in the same go. You highlighted in your title slide or something sigma naught and Doppler. Could you say a few things about what you see coming with the Doppler information over ice?
So ice moves at generally a much slower rate than the ocean. So a lot of the ice movement is going to be too slow to be observable directly by Odyssey. There's a cutoff of how low a frequency can move. However, near the ice edge, during ice growth in the first year ice, the movements can be very rapid. You can get 60 kilometers an hour in some cases of movement of the ice when it blows with the high winds under polar low conditions. In a few other cases, that will be observable. So the hope, and I might point out this is just a hope, okay, speculation if you prefer, that we'll actually be able to get some ice velocities in some crucial environments that right now we have no data possible at all, right along the ice edge during ice formation periods, especially in storms. Remember that polar lows, although they have clouds, they don't necessarily have a lot of precipitation. So we should have some capability for surface observation, even in these polar low storms, especially in the southern hemisphere, I think.
Thank you.
I don't know if it's a good answer.
And Christine, I think, is going to ask her question.
Hi. Yes, thank you, David, for this interesting talk. I have to apologize. I came in towards the end of it, so I didn't get all of it. So apologies about this, but I'll look forward to catching the rest. But you said that you were interested in the finer resolution that will get from Odyssea. And I just wondered if you could elaborate what are the sort of science drivers or the processes that might benefit from having finer spatial resolution, please.
Okay, so one of the examples I can present, if you don't mind me flipping that, are this ice edge image here. Okay, so this is a C-band observations of some synthetic aperture radar data, and we can see a lot of detail in this. But notice the ice edge itself is really quite finely detailed, the current scatterometer, even when we apply some of the resolution enhancements I've applied to it, are no better than a few kilometers, 4 or 5 kilometers. But Odyssey will have of the order of 1 kilometer to 2 kilometer resolution, which will enable us to resolve the ice edge, hopefully much finer. And now, because we get these multiple passes, we observe everywhere in basically the Arctic and the Antarctic where the ice edge is there, more than once a day, which gives us some really nice capability to do some dynamic studies of what's going on. I might point out that if we could understand the diffuseness of the ice edge, we actually get some information about the winds right there, right along the edge. Furthermore, the higher resolution will allow us to get winds close to the edge than is currently possible with existing scatterometers. And even SARs for that matter, because SAR has difficulty giving wind direction, especially near ice. And we'll be able to do that with Odyssey.
Okay. And if you were trying to push this to a space agency, how would you sell this? Saying we want winds and, we want to observe that edge to find a detail, and we want to have winds right at the edge. Why?
Well, a lot of gas transfer and nutrient transfer occurs right at the edge. That's biologically the most important area in the ice sheet. The sea ice area right there is right along the edge. That's where all these dynamic processes are coming. This is a little outside of my specialty, so I have to be a little careful how much I say about this. But the way I'm kind of selling this is, if Odyssey is going to be doing ocean winds, we get the polar science for free. That's kind of my point.
I totally agree. That's great. Thank you very much.
Thanks. I see that Momehel has his hand up.
Yeah, I hope you can hear me.
Yes.
It's more like a comment to what Christine just asked. I think there's an important quantity that's the flow size distribution, and so the Martian ice zone is really dynamically interesting, and we cannot model this right now because we do not know our state variables. And one of them is how big the flows are in the Martian ice zone. So exactly the zone you show here, we under observe, and we don't know what to do in models. That's how simple it is. But there's also waves coming in. But I think the pitch would be that it's a large area, especially in the Southern Ocean, where we unobserved the Martian area, and that's the dynamically most vulnerable part of the sea ice. Yeah, it's more like a comment. I basically had the same question.
A related question, if I may add a comment to that, would be, is the ice sheet, the sea ice tends to retreat, and there's less of it, especially in winter. It exposes the surfaces of ice shelves and glaciers to wave action. And the wave action then causes them to flex more than they would otherwise, and therefore has a tendency to weaken the glaciers that are right at this, and the ice shelves that are right at the edge, which potentially then could allow the glaciers to come down. So there may be an indirect effect, even in such a strange thing as ocean height, because it allows the land-based glaciers to more easily flow into the ocean. That's a process we're watching right now down the Pine Island Glacier.
Yes, so it's the combined thing, which is most interesting in the Southern Ocean, where small amounts of sea ice plus winds plus waves, that is only anecdotally there right now. But there's only true color images of Martian sea ice spiraling and eddies and so on. but what's actually happening there in the net effect is very hard to describe. But that's like if that balance flips the other way, the ice retreats. If that flips to freezing conditions, the ice freezes. And
Right.
Yeah, so that's why it's very interesting. Yeah, you see these effects there a bit.
Yeah, some of the interesting effects are when the adiabatic winds off of Antarctica push the ice away. You get a lot of Antarctic bottom water formation right there. But you can see that pulsing effect of those katabatic winds. And then as it melts back, you get another ice edge closer to the continent. And that becomes extremely important biologically for penguins in particular, and seals.
Yeah, thanks.
Thanks, Mommy. That was a great comment.
Yeah, if we can sell satellites on charismatic fauna.
That's what I'm trying to do here.
I wanted to ask, you mentioned water signals on icebergs being distinctly different from frozen ice. Does that have a diurnal signal so that in a sun-synchronous satellite, you see a difference in ascending and descending passes?
Well, now that's an interesting question. We can maybe study that one with this, if I can get it to start. There we go. So A68 is in the lower center right there, and you can see that it's bright white and it's not moving much. It's because it's so far south. But as it melts back, it's moving forward. This is a very sped up movie, obviously, up there. You'll actually see it turn black and it starts to go back and forth. That's the melt signal coming on there. Does it have a diurnal cycle? That is a great question. Now I'm going to have to go back and look at that and see if we can see it. We certainly see it when it gets far enough northward, but as we move far southward, there has to be, right near the edge of those melt events, there has to be a diurnal cycle. So that's an interesting science question, worth looking at.
It's certainly a challenge for mapping multiple satellites with different time of day crossings or even ascending and descending passes.
Yeah, I like to show these movies a lot because the wind is actually the noise in the process here for looking at the ice, which is the thing we normally look at. But you can actually begin to see the interaction of the wind with the ice as well when you see these things, even though it's a little sped up for that. But yeah, see the kind of the really interesting stuff when the ice starts to melt, where as it melts, the wind starts to push it. You get all these fingers produced and stuff, and it's totally fascinating. We've actually used the iceberg movement because it tends to be embedded in the current as a current sensor, an in situ current sensor for the deep water, because they tend to be quite deep. These large icebergs extend 600 feet or 600 or more feet deep.
That leads to one additional question. How much do you see motion of tides or near inertial oscillations in the ice motion?
I can't answer that question. I don't know that
not very well sampled.
I don't think we're very well sampled to do that, but that's a good question. It must be there.
I guess I'm looking at your image flashing on the screen and thinking it's got this oscillation, which could be some combination of tides and near inertial oscillations and winds and prevailing current. And
so at least
how
part
do you
of that,
disentangle that?
well, part of this is due to the fact that it's fronts. You know, there's a tri-lobe frontal system that moves around Antarctica, and that affects the katabatic winds, which causes that pulsing that you see right off the Ross ice shelf, in the Weddell Sea down there. You see how it kind of produces those lines as the wind pushes that off. That's actually due to that movement. The circulation around Antarctica, the atmospheric circulation, drives that, and so there is a coupling between the ocean north of Antarctica and this pulsing that we see is the winds push. The katabatic winds are free. They kind of move around the continent a little bit, pushing this way and then that way. That process, is, to my knowledge, is not well understood. And there's not been a lot of data to study, but we can see the evidence of it quite clearly here. We ought to get some more oceanographers looking into that. Polar oceanographers, yeah.
Yeah, really cool. And as Christine pointed out, important to figure out what the selling points are to make a case for pursuing it all.
Yeah, so I've done a sort of a sampling here. There are papers associated with these things, but this idea of extracting cellular point for polar science is one that we could really pull in. There's a lot that could be done here. I'm just one of several people working in this area, but there's got to be more. Could we come up with some good selling points?
Yeah. Are there other questions today? Mami has his hand up again. And
Yeah.
Fabrice again.
I'm first.
You're first.
You had a slide on surface roughness over ice, so that you can see the wind direction of the ice. And I wonder, so you said like you're limited in time in temporal resolution, and this is like, does this get better if you have a high resolution? And is this fed at all back to the like assimilation system, like to state estimates or to reanalysis?
Okay, let me take your question, kind of split it into some pieces here a little bit. The mechanism by which we can measure the wind is the wind-induced roughness on the surface. Okay, that is a process that's not instantaneous, unlike in the ocean where the water within moments, minutes at the very least, at the very most, becomes wind roughened. It follows the wind, and they become I've forgotten the word all of a sudden. They follow each other. Yeah, very quickly in the ocean. There's a very quick response, and they become coupled very quickly. That doesn't happen in the snow. That process requires an extensive amount of time for it to move enough snow around. So what we end up seeing are averages of the wind flow over fairly long time periods. This process is not understood at this point or very well modeled that I'm aware of. So when I talk about temporal resolution, I'm really talking about the temporal resolution of the snow, which is actually like a low pass filter for the winds that are occurring over it. I believe, however, that if we had at a higher frequency to see the smaller scale roughness and more frequently, we might be able to see the changes the wind embedded on top of this larger scale general snow dunes that are produced in Antarctica. We did a similar study in sand dunes, looking at winds that produce ripples on the surface of sand dunes. And there we could see seasonal effects very clearly in the data. We haven't done as much in Antarctica because there kind of aren't seasons in Antarctica so much. In Greenland, there is evidence of seasonal variation in the wind direction and the ripple intensity up in Greenland. But that's studies that more work could be done on.
Okay, thanks. But if there's less seasons in Antarctica, you have a higher chance to see the trend, which is pretty interesting in terms of atmospheric circulation changes.
Agreed.
That everywhere else very noisy, but they're pretty steady.
So the katabatic winds, in principle, are always flowing down of Antarctica. But when there are large fronts that couple down into Antarctica, that push air, the northern air down in there, it changes the katabatic winds, and that's what causes that pulsing we saw in the sea ice.
Yeah, that's why it's very interesting. Like this,
I don't know what studies have been done on that.
Nearly none.
That's what I'm assuming. I haven't found any. Yes. But that's an area somebody can go into. It's just I can only do so much myself, so we've got to recruit some more people to do that.
Yep. Thanks.
I see
Fabrice?
Yes. So going back to icebergs, so I've been looking at iceberg effect on waves, and I was fortunate to work with Jean Tournade on the statistics of small icebergs. And I was wondering how far you can push the resolution to detect the icebergs, and how we may be able to extrapolate ODC resolution to the size of icebergs. And the question that goes with that is, of course, then there's some that you don't resolve, and they're going to contribute to the sigma naught, and possibly will result in artificially high wind speed. So I was wondering if you looked into any of that, because usually when the big icebergs break up, they shatter into many small ones. Yeah, maybe there's too sparsely, so we can see very nice in like SAR imagery. And I was wondering what kind of a bias you would get in wind speed from that. And yeah, just,
So I've done some, I'll have to answer for me personally on this one. So we've done some work on this where we've looked at the backscatter values along near the sea ice and of course near icebergs, and it'll contaminate it.
Right.
And I've seen, your work on the altimeter detections. You've got some really nice work looking at the statistics. Well, the Odyssey resolution of 1 kilometer is enough to start resolving these smaller icebergs as icebergs. So we will be able to then say, hey, there's an iceberg here, the area around it. We can then apply these sea ice type contamination principles using the Odyssey data that I believe we could actually then answer your question, which right now that's almost impractical to do with the data because it's so coarse for most of the stuff. The altimeter data is, even is finer than the scatterometer data, which makes your
just
studies,
statistics you can do from that, yeah.
Statistics viable, but it's hard to do that with this work. So in this, it's a little bit hard to see in this figure in the lower right. I put it in there just because it was a fun thing with the 1700 data. But if you look carefully, you can see there are actually 2 colors present. There's a dark red and a light orange. The dark red are larger icebergs that are part of BYU's iceberg database that we extract icebergs from there. The smaller database comes from in situ observations made by dropping buoys, markers on buoys, GPS tracking systems. And we can see that they match. Some of the icebergs are the same ones. We can also see they extend out a little further to the right. The circulation that goes clockwise around Antarctica. I apologize for the small size of the figure. I can't do much about that in this environment. But they extend further because when we lose track of them, some of the buoys continue with the icebergs further. With the Odyssey data, we would be able to extend the sizes to much smaller icebergs, and that tail that goes up and to the right, you kind of see a hint at it, would be get more of it. Our data show that 95% of all large icebergs go through the Weddell Sea and get ejected into that tail. There are exceptions. You can see them moving off to the right and some down to the lower left. Odyssey will help us to be able to understand that distribution a whole lot better because we don't get them. So we can take your statistical stuff, Fabrice, and extend it. And this will be a really nice validation for both the approaches. I'm really excited about this possibility of being able to see small ones. And then to look at wind contamination due to the icebergs and the breakup of that, we can begin to analyze that. That is an interesting question. We don't know what's going to happen for the growlers and the meter-sized bergs that occur because they don't have a whole lot of surface expression, but they will suppress the wind spectrum.
Yeah,
I'm wondering if the Doppler will be helpful in that area because we'll see the Doppler area right around the icebergs, and we'll be able to say, "Hey,
Doppler versus sigma naught." Yeah, okay.
This will be an important area. I think it's a whole science area that you work up. Your work will just be really nicely extended by having this extra data.
Cool.
And I think this idea of using the both the Doppler and the backscatter to sort of see where we have contamination due to icebergs and the debris that comes out of it are going to be an important way to make sure that our Southern Ocean winds are not contaminated by iceberg pieces. But we can see, even from this simple plot here, that the Southern Ocean that is to the west of South America there, that area doesn't have a lot of icebergs. The Southern Ocean right south of Australia does not have a lot of ice. We'll be able to get all the way down to the ice edge, the sea ice edge, without a whole lot of contamination, just based on the historical databases. So it's nice to have this data to sort of draw a few conclusions of where we need to be looking carefully.
Thanks.
Yeah, really nice. Other questions from anybody before we close?
I like to think this is a cool research topic, but that's a pun.
Yeah, well, this is really great. Thanks a lot. I'm going to stop recording and